Good morning. Thanks, Bill, Lindsay. As Bill mentioned, I started in Cairo, Egypt. I'm still a professor on leave in Cairo University. However, I'm here with Applied Science International. I actually came today from North Carolina. So this is, Martin, would you like to play that video? This is the kind of thing we do, the computer simulation. So this is what we all hope our projects will go like. Most of the time this is what happens, but we all know that we have challenges or hazards that we have to plan for. And today we're discussing performance-based planning of your demolition. So you have some possibility of impact with a neighboring structure, possibility of separation of a structural component, incomplete failure, overloading due to some demolition equipment. These kinds of troubles, these are the things that make us worry all the time. And I'm here to discuss how we could lessen our worries, make them less. So we have a new technology called extreme loading technology. It's based on a method for the structural engineers in the room. It's called the applied element method, similar to the finite element method to some extent, which this method originated in Tokyo University in 1995. And since then, it has been picked up by many European, North American, Australian, and Asian universities all over the world. They're working with this technology for structural analysis, but it has also been picked up by demolition contractors, especially all over the world. Some of the contractors here in this room, Fabio Bruno from Brazil, Liberty Industrial from Australia, many US demolition contractors have worked with us using this technology to make sure we have the best plan for our demolition. So the advantage is you get to model three-dimensional model of very detailed components. This here is the I-35 bridge, and this is just one connection of that bridge. We built a whole model for the whole bridge. And this is the level of detail. Each and every bolt and rivet, you can model it in the simulation. If you have a connection at the base and you're going to have an anchor bolt like that, you include that in the model. If you're going to change and make some changes and take the anchor bolt out, you can actually take this anchor bolt out of the model. So this level of detail, if you are going to cut just the lower part of the flange, you can model the flange with the lower part taken out. And this level of detail using this technology, it's possible to do it much faster than we used to do before. And you take this level of detail and you incorporate it in the whole model for the whole structure. So this is an imaginary weakening plan for a whole structure and strengthening as well. So you put in whatever struts that you have. Every mark that I have here is a detail similar to the details I just shown. Some part here is cut, some part here is added. If you have non-structural components in your model, additional weights or equipment that you're worried might be damaged, or if you have a tank that has some hazardous material, all that we can put inside our model, so you don't have many of the guesswork that we have been doing by instinct or by experience. We can actually put it inside the model. So weakening, strengthening, non-structural components, and again, some of the level of detail for the modeling, like this is the standard detail. If you have a V-cut here, a flat cut here, that kind of thing, we can put that in each and every column that you're concerned about. This is, for example, a picture from one of our models. This is a double eye section, and we removed part of the eye section. If you have this kind of detail and you're cutting just a diagonal cut on the flange or on the web, we can cut just the flange or just the web or both, depending on your plan. If you have the implosion sequence, if you're going with an implosion and you're taking a certain column at a certain time, we program all that into the technology that we are using. So you would be able to say at this point in time, this column is being removed. At this point in time, this column is being removed. And the result is what we've seen in the beginning. You are able to get, these are still pictures from the video. So you are able to get matching prediction. And what we almost always do is release this to clients, to all stakeholders, the video before the actual demolition happens, so that you can assure everyone this is what's going to happen. And as we'll discuss later, we can also deal with some uncertainties that we have to face every day. So this is the model, and this is what we actually got when the demolition actually happened. If you have sensitive structures nearby, like this is the structure you're demolishing, and you have different sensitive structures at different places nearby. You can include them all in the model, and you can say, okay, what's the level of vibration at this specific structure? Is it acceptable or unacceptable? And this is where I'm speaking about the performance. You just can check the performance and see how it works. So we can create actually a model. This is a half model for the whole soil below the structure. So sometimes we can get that, like the soil log, the properties of the soil, and we can include all that if necessary in the model, the different layers of soil that you have. And then this is the location of the impact, and we can say, okay, up to this distance far off, this is the expected level of vibration. This here is a tower that was part of a bridge in Texas, and while demolishing that, two impacts with the ground happen. So first, the lower deck hits the ground, and then another impact happens when the top part of the structure hits the ground. And when we put that into our model, we get two impacts. A smaller impact at the very beginning at maybe 2 or 3 seconds time here, and this is when the deck, the first part, hits the ground. And a much larger impact when the top part of the structure hits the ground. And we can take this force and again feed it to our tool or our software, and again we can go and say, okay, so Martin, can you please start the video? So we can see, oops, let me go back. Video again. Okay, so we can, oh my God. I just keep hitting the wrong button every time. Okay, so I need the pointer, yeah? Here it goes finally. So this is the vibration propagating through the soil. And we can measure the velocities at different locations here, the chart down below. If you hit play one more time, the charts down below give the maximum vibration at different distances from the structure. So we can say, okay, this is the maximum vibration at this point, and this is the maximum vibration at that point. So this is the kind of thing that you can do if you have sensitive structures, we can create a chart like that. The white zone here is the safe zone. Oh, sorry, the unsafe zone. The white zone is the zone where the vibration is above the limit. So this is basically your exclusion zone for any sensitive equipment. And as you see, depending on the shape of the front hitting the ground, it's not necessarily a circular zone. It can have different shapes depending on what's hitting the ground and when. So this is something that we can get out of this tool. We can estimate the debris field. Oftentimes, the demolition contractors are worried about how far is the debris going to spread. So we can go and estimate. This is the distance that you expect for the debris based on where the model settles at the end. So this is a quick overview of the technology. And this is how we usually would have a demolition project go so that we achieve the best performance, again, with optimization of the cost. So we would like have a site visit, meeting with the client, as much as possible, the structural data, the drawings. We can have soil data if possible. We identify all the potential hazards with all the stakeholders, the proposed plans by the contractor, any performance requirement that the contractor or the client is worried about, and we take as much as possible of that, depending on what we have. And we can put that into a three-dimensional model. And then on that model, we put all the weakening, all the strengthening, anything that has been envisioned by the design done by the contractor. And we run the analysis and verify that this is the first of all, that the structure will be safe, retain integrity until the demolition time. And then we can check for lateral loads, wind loads, seismic or earthquake loads. And then we can go and apply the demolition scenario. And at all points along this stage, when we're doing the analysis or running the different scenarios, we always go back and check the performance measures. Okay, does it satisfy the requirement performance measures or not? And then we can go back and modify if necessary. And if once all the stakeholders are happy with the plan, they've seen the videos for what is expected to happen, we can go and submit the final results after they see the three-dimensional model, the different scenarios that are going to happen, the vibration analysis if necessary, that kind of thing. So this is how we would work with you. Can you please play the first part of the video? So sometimes you have worries about things like a diagonal strut that you put there, and you want to see what's the dynamic force in this strut as the structure fails, whether it's going to fail prematurely or not. Or you're worried about that you have squatting. These are some of the challenges that you face. These kinds of things we can go and model, or whether you'll have overloading or impacting with a neighboring structure. So I'll just go through some of the examples of things that happened in the scenarios that we've done, and so they didn't happen in the real life at the end. So this is the best thing that we can do. Have all the accidents happen in the simulation rather than happen in the real situation. So I'm just going to show a series of accidents that didn't happen. So this is one case. Again, play, please. So this is squatting or incomplete failure. So you see, can you run it one more time? You can see it's this is an industrial structure. It was being demolished by pulling using excavators. And one more time, please. Instead of failing completely, it just shortened by one level, and it didn't go all the way. And this is what happened in the scenario, but this is not what happened in the real life. We modified the scenario to avoid this case. This is another case. Did I skip 2 slides? No. This is another case where the demolition contractor is planning to use skid steers or bobcats on top of the slab. And again, worried about how many bobcats can I put there safely. Obviously, the contractor wants to put as much as possible without damaging the structure. And you were worried about the interaction, like the dynamic loads of bobcats on one side or on the other side at the same time. What would happen? So if you play the video, like we would put in the model the different bobcats going around, and then we try all different combinations to say, okay, this is the maximum vibration that you get, and this is the worst case. So as structural engineers, we used to do that using like a static analysis, which is fine, but this is a new tool in our set of tools. We can do this dynamically, and we can optimize it more if we are able to put it in a real live model, a three-dimensional model for the bobcats moving on top of the slab. The possibility of failure in the wrong direction, like this structure, it started to fall this way, and then it goes and folds backwards like that. Again, this is a scenario that did not happen. It happened in the model. We changed the scenario in cooperation with the demolition contractor, and in the final scenario, we didn't have this problem. So that's another thing that this technology can help you with. This is another one using just, this is another industrial structure that we were also demolishing, again using pulling. And again, just over here to the right is a sensitive structure. So again, we were concerned that it might hit it, and this is actually what happened in one of the scenarios. It started falling the right way, and then because of the weights were distributed, and if I go back here, like the structure had a peculiar distribution of weight inside the structure, which led to the structure at the end. When it hit the ground, it folded backwards. So this is something that you don't want to happen, and this is a scenario that did not happen in the real life. Another case, okay, now the same structure, it's falling the right way. We got it to fold the right way. So it's moving forward. We changed the scenario, and it's moving forward nicely. But what's the problem you see here? The problem is this structure had the top beam, instead of being supported by the structure, it was actually supporting the whole structure. The top beam was acting like a support, and everything was hanging from the top beam. I have a slide later that shows that. So they had those hangers here, and the whole structure was hanging from this very heavy top beam. So the problem was this top beam separates. It separates like that. And the problem with that is, instead of having the structure end up right about here, this is where you want it to end, and this way the maximum impact happens at this point. If you look at this screen here, this is where I expect the impact to happen. But because of this separation, the impact happens here. And just over here, we had another sensitive gas line, and we didn't want any impact to happen at this point. So we had to ensure that this top beam does not separate. This is the kind of thing that you could plan for. So you put your performance objectives and you plan for that kind of thing. So again, you can do recommendations, many recommendations. Additional welding, for example, is one solution. Weld more to make sure this beam does not separate. You can put cables to tie that top part, so when it separates, it just stays attached. It doesn't tip over like that. You can come up with many solutions once you've realized or noticed the problem might happen. Finally, one issue that bothers us all and challenges us all the time is uncertainty. Oftentimes, we don't have structural drawings, or we have structural drawings that have been modified, and the real structure is not what you have in the drawings. You have old structures, the drawings have been lost for a long time ago, and you have to deal with what you have. So you go, you make as much visits to the site as possible, you test, you try to find out what's the properties of the material at this point, but you still get surprises. Obviously, this is not the best of work, like this is not work that any contractor here would do, but still it is a surprise. The guy kept, with the excavator, he took out one column, the structure is still standing, he took a second column, a third column, he took out 11 columns all around the structure, and the structure, it just didn't want to go. Some of you might point out some of the reasons, like now that you see it, you can say, oh yeah, this part here is acting like a deep beam, and it allows it to cantilever in all directions without failing. The fact that there isn't much weight at the top here is helping a lot. But instead of discovering that after the fact, the idea is you do a simulation for the actual thing with all the non-structural weight, with everything that you have here, all the masonry walls, depending on how detailed you want this to happen. But you do that prior to the analysis. This particular contractor never hired us, but but we've had similar work with other contractors. This structure here in Brazil, we've done with Fabio Bruno, and just neighboring to that structure, they had a school and a church, and it was very close, and again, it was an old structure. The available data is not enough. You go and you test as much as you can, you see the properties of everything, but still the amount of available data for a structure that is 60 or 70 years old is not enough. So we have a model for the whole thing, and we make some assumptions. And we change those assumptions, and the advantage is it doesn't cost much once you have the model to change the assumptions. It's about like 6 or 7 hours, depending on how big the structure is. If it's like a moderate sized structure, 6 or 7 hours of work, and you get a different scenario, depending again on how detailed your scenario is. But we tried different things. Okay, what happens if this is highly reinforced concrete, or just 4 bars in that column? Or this column is made of masonry instead of reinforced concrete. Old construction, you find all strange things when you start ripping apart the structure. People did in the past many strange things. You can't understand why they would have this, but sometimes it happens. So we tried different scenarios, and we wanted to make sure that the best scenario is everything goes this way. If there is a chance that the structure will fall in the other direction, that's what you don't want to have. So we identified a couple of scenarios which had a problem like that. So you would have a very good hinge down here, which this is where you want the structure to fail so that it hinges and falls that way. But depending on how this reinforcement is, you can have a second hinge here, and then you have a part that would fall in the wrong direction. You have 2 hinges along the same column, and part of it is going to fall the wrong way. And then you identify this is the worst scenario that could happen, and then for that scenario, you go and be creative. All of you can come up with different solutions to avoid that, but once you realize the problem is there. So you can, one scenario is you like tie a bunch of cables here, make sure this part goes with the rest of the structure, it doesn't go separately. This is the part that's twisting the wrong way, let's bring it with the rest of the structure. If that, because we have something that's uncertain, we're being extra cautious, but if that's the cost of avoiding an accident, then by all means, it's definitely worth it. So to sum up, whatever the method you plan to use, whether it's skid steers, high reach excavators, wrecking balls, any weakening or strengthening plan that you have, if you're doing implosion or pulling using cables, all the different demolition techniques, we've found that cooperation with the demolition contractor for planning the scenario and having a 3-dimensional model, as much as possible data in that model, regardless of the case, would result in optimization in terms of the time for doing the work, avoiding to redo stuff or having delays due to unexpected things, and the cost is definitely a fraction of what you would have if you have any unexpected mishaps, and you achieve the performance objectives that you're looking for that are required by all the stakeholders, whether it is the housing authority, whether it is the client, whoever, like whatever performance objectives that you have, you can put them into your planning model. So with that, I thank you all, and I think questions will be at the end as well. Okay, thanks a lot.